Hi everyone, I am Kushwant Kumar Ponduri. Today I am going to discuss about extensible language aware merging. The authors of this journal is James Hunt and Walter Ticky. It is published in the journal IEEE and the citations are 40. In modern software development, it requires the coordination of a new development with ongoing system maintenance. The systems like revision control and configuration management provides mechanism for combining different changes. In line-based comparisons, it mostly uses a text format because it's fast and accurate. But coming to the results, it is a bit slow. Mainly for merging, we need accuracy, applicability, and performance should be accurate and high. To overcome all these, to provide better results, others has introduced extensible language-aware merging. In this, we have different types of algorithms. The one is the line-based algorithms, other one is process-based algorithms, and the structure-based algorithms and semantic-based algorithms. In line-based algorithms, the methods remain the standard practice in software industry. It's a method, it's a standard practice method which remains in software industry for merging. It is very cost effective comparing to the remaining algorithms. And coming to process-based algorithms, Mr. Lippi made an attempt to produce better merging by requiring the editor to be smart. The approach has advantage that some conflicts resulting from syntactic changes which has no semantic effect, and the cost is a bit high comparing to the line-based algorithms. And coming to the structure-based algorithms, it falls a midway between the semantic and the line-based approaches. In order to calculate the difference between these two revisions, each one is parsed or divided into three syntactic structure of the program code. And coming to the semantic based algorithms, a true semantic algorithm concerned depends on the program compiling, not on the program how it is written. Most of the work in this area has been done by the team of Miss Horwitz and Messrs. And Binkley, Yang and Prince. In line-based algorithms, there are two main difficulties. They are irrelevant to the meaning of the program, like reformatting can make the output unusable, and some kind of conflicts are missed. For example, when a variable is renamed in one variant and the line is added in the other variant, in this case, though the variable name from the second reference is wrong, or no conflict will be flagged. The structure-based algorithms are not as complex as the semantic methods, but the results cannot be disturbed by reformatting, as is the case with the line and character methods. And in line-based methods, it is very comparing to remaining three, it's very cost-effective. Remaining three algorithms are very costly comparing to line-based algorithms. In design and implementation, the process is as shown in the figure. In this, the parser divides data into sets and passes to this analysis phase. In this, the analysis is done and it passes to the merging, and the merging is done in this phase, and the output is produced. The data and the data flow is done from left to right, where the invariant and variant 1, variant 2, where data is given to the parser. In this, the symbol analysis, all the analysis is done in this in this phase. It improves on structural based merging by using a more sophisticated differencing algorithm and including some semantic information in language dependent form. First, each of these input revisions, a common ancestor revision, base and two variants will be there. Thereof, left variant and right variant are parsed and analyzed to determine which tokens are symbols and what attributes they have. In left variant and right variant, the data is parsed or divided, and then it passes to analyzation phase to determine which tokens or symbols and what attributes they are present in the given data. The merge algorithm itself has three phases. It is integrating remainings from which each variant into other variant, and the next rough merge, building a rough merge from variants, and then resolving apparent conflicts with semantic information. Renaming integration is carried out directly on the change list. The second phase generates the first merge list. Finally, the resolution phase removes conflicts by combining the changes from both the left and right differences contained in the conflict blocks of the given merge list. Coming to integrating renamings, we have two kinds of changes. They are of interest, pure name changes and the signature changes. As long as only the name of the given identifier is changed in one of the variant, there is no conflict. If there is a change in both of the variants, both may be rejected without changing the semantics of the final program. And coming to rough match, the algorithm calculates the rough match in a single pass through the two differences. The algorithm relies on finding corresponding unchanged blocks in both differences and using these as reference points for the match. And we have different compatible types like compatible, signature compatible, name compatible, reference compatible, and incompatible. Incompatible where two nodes with this attribute are always compatible with other two nodes, and in signature compatible where two nodes with this attribute must differ in name, argument type, and number to be compatible. And coming to name compatible, two nodes of this type must differ in name to be compatible. In reference compatible, these nodes are compatible when the set of impure reference in their subnodes are disjoint. In incompatible nodes of this type can never be combined. In little semantics, the goal of this phase is to reduce the number of apparent conflicts included in the merge. The strategy is to segregate the code sequences into classes according to the difficulty of determining whether it is two sequences interfere with one another or not. In this figure, the left alternate and right alternate, and then the output is shown in this figure. Whereas in left alternate and right alternate, if we observe there are two common, if there are any two common attributes, it is combined into the single, or it is merged into the single attribute. Where we can observe that unchanged A, and right alternate we have unchanged A. It is merged into the single attribute. If we have any conflicts in any of the alternates, then it will be merged into the single conflict in the given output. If you don't have any attribute in the left alternate or right alternate, and the conflict will be deleted. In this decision table, uh, the start point in the base of aligned token string is used as the next alignment point, and the last position of the aligned token is used as the last alignment point for the next iteration. Once alignment is established, blocks are added to the merge to reflect the changes. It is clearly going to evaluation. There are several aspects of the system to evaluate: format independence, name change propagation, and collocated change resolution. Format independence is exhibited when disjoint sets of add or remove or change of code any operation is performed. It can be integrated even when one developer changes the formatting of entire software document. Collocation resolution refers to the process of determining whether or not changes made in both variants of software document are which are compatible, and hence both are allowable, or if they do in fact, or if they conflict. The example of base decision table is clearly explained. First, in base we have declared a class, and we have given a variable value, and which returns the variable stored the data stored in the variable value. In left variant have some data, and right variant have some data, and here we have matched the left and right variants. The result produces like uh, here we have given the variable FOO, and where the value of this right variant will be loaded into the variable FOO, which returns the value by calling the function set FOO. In left variant, we can see that the value will be returned that is stored in the FOO. In coming to right variant, the value will be returned which is stored in the variable value. By merging that directly, we can load the data in the value to the FOO variable, and we can get the output by calling this function. The conclusion is this algorithm is a new algorithm that provides better trade-off among performance, applicability, and accuracy. Because for merging, the main we need is the performance, accuracy, and applicable to be accurate. On the other hand, the extensible language aware merging has wider applicability than current full semantic approaches. This algorithm achieves the main goal of providing full syntactic merging with some semantic analysis in acceptable time. The references are J.J. Hunt, Extensible Language Aware Differencing and Merging, PhD thesis, University of Carleton, November 2001, and another reference which is in 1998. You can go through these references. Thank you very much.